Hi everyone, I'm Marc. Thanks very much for watching our video. This is joint work with Johannes Schmitt from the University of Bonn and with Philipp Wellnitz from the MPII at Saarland Informatics campus. You see the title is quite long, definitely too long for a short video, so let's only talk about a subset of what we actually did, namely about the complexity of the problem of counting small subgraphs. More precisely, we will be interested in counting subgraphs with k edges. Formally, given a graph property phi, a positive integer k, and a graph G, we will be interested in computing the number of k-edge subgraphs of the graph G that satisfy the property phi. And we denote this number by sharp edge sub phi k to G. For example, if phi of h is 1, if and only if h is a matching, that is disjoint union of edges, if k is 3, and if G is this graph, then the answer would be 5, because there are precisely 5 3-edge subgraphs in G that satisfy this property. In this case, those will be just the 5 3 matchings. As another example, consider the property of being acyclic. Again, k is 3 and G is this graph. Then I didn't list all of them, but here are some of them that are acyclic. So again, the 3 matchings are acyclic, but also this graph here and this graph here are 3-edge subgraphs of G that are acyclic. Note the subgraph are not necessarily induced. As a non-example, this triangle here would be not an acyclic 3-edge subgraph of G. We will use the following notation for functions in this talk. So I will substitute the graph G by this star here to say that this here is a function that expects as input a graph G and then outputs the number of k-edge subgraphs of G that satisfy phi. And we will analyze the following family of problems. So given a graph property phi, the problem sharp edge sub phi expects as input a pair of a graph G and a parameter k, and the goal is to compute the number of k-edge subgraphs of G that satisfy phi. Note, this is important here, phi is not part of the input, but part of the problem definition. Therefore, every property phi defines a new problem. And our goal is to understand the complexity of this problem depending on the property phi. More precisely, we want to know for which phi this problem is fixed parameter tractable, for which phi it is sharp W1 hard, or for which phi it even allows a conditional lower bound, such as not being solvable in time f of k times the number of vertices of the input graph to the small o of k. Okay, if you don't know what sharp W1 is, just think of it as a parameterized counting equivalent of NP. Okay. We are not the first ones to study this problem, so let me tell you something about previous results on this problem. An implicit consequence of a result of Kotikapia and Marc's states that for any property phi, you can solve this problem in time f of k times the number of vertices of G to this exponent, which is linear in k, but the constant in this linear function is quite small. So while the k is here still in the exponent, so it's not FPT, it is still much better than the brute force algorithm. The brute force algorithm runs in time roughly number of vertices of G to the k, or number of edges of G to the k. It is unsurprising that there are hard instances of the problem. For example, if we choose phi of h to be 1, if and only if h is the clique, then this problem here basically encodes the counting k-clique problem, which is the canonical sharp W1 hard problem. Also, for some other properties, such as being a tree or being a forest, this problem was shown to be hard in the past. There is also a conditional lower bound for the property of being a matching. We have seen this as an example before. In this case, we know that it's sharp W1 hard, and it cannot be solved in time f of k. times the number of vertices of G to the small o of k over log of k for any f, unless the exponential time hypothesis fails. And this is due to Kotechapian and Marx. For some specific properties, we actually know a complete complexity dichotomy. So for this certain set of properties, which I will define in a moment, we know that this problem is either FPT or sharp W1 hard, and we know a precise criterion that is necessary and sufficient for sharp W1 hardness. There are examples of those properties, but formally, the properties to which this dichotomy theorem applies are those that satisfy that for each k, at most one k edge graph satisfies phi. This is, for example, true for the property of being a star or a cycle, but also for the property of being a matching or a clique. The entire dichotomy follows by a line of work starting with Froome and Coe and then continued by Kotechapian and Marx. Now, what did we show? We gave a complete complexity dichotomy for properties that are minor closed. So this is one of our results, one of our main results that states whenever phi is a minor closed property, such as planarity, then, okay, first the easy cases, if phi is trivially true or of bounded matching number, then the problem is fixed parameter tractable. And by bounded matching number, I mean that there's a constant, let's call it C, such that every graph that satisfies the property phi has matching number at most C. And indeed, this part here does not only hold for minor closed properties, but for all properties, and was known before, or at least follows directly by prior results. The important thing is that we proved that for all other minor closed properties, we get sharp W1 hardness. And additionally, if each forbidden minor of the property has a vertex of degree at least 3, then we cannot solve this problem in time f of k times the number of vertices of G to the small o of k over log of k for any function f unless the exponential time hypothesis fails. And now note, this is already the second time where we have seen this strange bound of small of o of k over log k in the exponent, which is not entirely what we want. But this is actually not an artifact of our proof, but this is related to some major open problem with parameterized complexity. But still, this shows that any significant improvement over the brute force algorithm is unlikely. In this talk, or in the remainder of this talk, I will give a sketch or an overview of how we can prove such a result, and I will focus towards the end on the property of being planar rather than on like any arbitrary minor closed property. I will also only talk about sharp W1 hardness, but not on how you get the ETH lower bounds. Okay, the most important ingredient is the so-called complexity monotonicity principle that was introduced in a breakthrough by Kotechapian and Marx a couple of years ago. Intuitively, this framework states that whenever you want to compute a finite linear combination of graph homomorphism counts, then this is precisely as hard as computing its hardest term. We will see in more detail what this means formally later, but first you might ask why this is related to our problem. And the answer is, it is because we can express the number of k-edge subgraphs that satisfy phi as such a linear combination. And after we have done that, we can analyze the coefficients of this combination, and then we will see that this principle allows us to determine the complexity of our problem by relying on known complexity results of the problem of counting graph homomorphisms. To this end, let me do a quick recap on what graph homomorphisms are. Given graphs H and G, a graph homomorphism from H to G is a mapping from the vertices of H to the vertices of G that is edge preserving. We will use, again, the notation with a star to express functions. That is, I write sharp hom from h to star for the function that expects as input a graph G and outputs the number of homomorphisms from H to G. But let's take a look at some examples. If this is our graph H and if this is G, then this is the image of a homomorphism because it is clearly edge preserving, this as well, but also this. So homomorphisms do not need to be injective. So we could map those two to this vertex, but this would be a non-example because we don't preserve that edge here. And even in this small example, we already have 160 many homomorphisms. Now back to our problem at hand, edge sub. First, we show, and this is actually just a statement of existence, this is actually quite easy to show, that for every phi and k, there exists a function a phi k, such that we can express the number of k edge subgraphs that satisfy phi as this linear combination of homomorphism counts. So we take the sum over all graphs H, then take the value of a phi k of H times the number of graph homomorphisms from H. And we can also show that the function a phi k has finite support. That is, it is non-zero only for finitely many graphs, and therefore this is indeed a finite linear combination. And in what follows, I will just call this a phi k of H to be the coefficient of H. And then, using complexity monotonicity and known results on graph homomorphism counting by Dalmau, Johnson, and Marx, we get that if there is a graph H such that H has high tree width and a non-zero coefficient, then the computation of this linear combination and thus our problem is hard, and otherwise it is easy. I won't define what tree width is in this talk because we only need it as a black box. Just think of it as being a measure how tree-like a graph is. Now you might think, okay, we have this linear combination, and we only have to check which coefficients are zero or non-zero. We should be almost done. But actually, everything up to this point is the easy part. The hard part and the major technical difficulty of this work is to prove which coefficients are hard and which coefficients are zero and which are non-zero. And it turned out in the past for related counting problems that those coefficients sometimes actually describe known algebraic and topological invariants, such as the reduced Euler characteristic and the H vectors, also the weight enumerator for monotone Boolean functions. And I won't define any of them, just if you've heard of them before, you see that there's actually something going on with these coefficients. Unfortunately, proving that any one of those is non-zero is quite hard. So we cannot hope to get like an easy condition on finding out when those coefficients are zero and when they are non-zero. But in this work, we found out that we can actually analyze the coefficients of low-degree Cayley graphs quite easy. So what is a Cayley graph? Given a finite group gamma and a symmetric set of generators of gamma, the Cayley graph has as vertices the elements of the group and an edge between x and xs for every element x of the group and every element s of the symmetric generating set. This graph has no self-loops and no multi-edges, and since S is symmetric, we also assume the edges to be undirected. For example, and this will be the most important Cayley graph in this work, we can consider toroidal grids, where the group is the direct product of the group with p elements for prime p. That is, the elements are pairs between 0, 0 and p minus 1, p minus 1. And we take the four generators plus minus 1, 0, and 0 plus minus 1. And then this graph will look like as follows. So if we have an element here, xy, in this group, we can go up, which corresponds to adding 0 plus 1. We can going down, left and right. So those four directions precisely correspond to the generators. It is called toroidal grid because if we draw it differently, we see that it's actually torus. And this will be actually important later. Okay, so let's go back to our linear combination. we prove the following, and I need to disclaim that what I'm about to show you now, we actually proved for a colorful version of this problem. However, the colorful version is interreducible with the uncolored version, and it is out of the scope of this talk to now include also the colorful version. So just keep that in mind, that we actually prove what follows for a colorful version of this problem. For technical reasons, we do that. So we prove in this linear combination, if H is a Cayley graph of P group gamma for prime P with K edges, then the following holds. So let's go over this step by step. The coefficient of this Cayley graph is congruent to this term modulo P. And how does this term look like? Okay, we take the sum over the partitions of the generating set with some side condition. I will talk about this side condition in a moment. But for each partition included in this sum, we take -1 to the number of blocks -1 times the number of blocks -1 factorial. And yeah, even without considering the additional condition here, the nice thing is that the number of terms in this sum only depends on the number of generators. It is independent on the size of H or the number of edges of H. And this is what makes it feasible to analyze the coefficients. Okay, now let's take a look at this side condition. I write here if phi of this thing here, which we call the fractured graph of H and sigma, is 1. I won't define the fractured graph formally, but I will just give you a picture, and I hope afterwards you get some idea what those fractured graphs are. So first, we take as example our toroidal grid, which has a generating set of size 4. So we will have 15 different partitions, and each partition yields a graph. This graph is obtained by splitting the vertices of the toroidal grid according to the partition we are considering. So for example, in this partition here, we have 3 blocks, 1 for up, 1 for down, and 1 for left and right. And therefore, each vertex is split into 3 vertices. 1 is connected to the upwards group, 1 connected to the downwards group, and 2 and 1 is actually corresponds to both directions, left and right. So this is connected to the left and to the right. And then actually each of those partitions or each fractured graph has a quite nice shape. I said before, we only have 15 ones at most, which is very nice. Let's take a closer look at the form of those graphs. The trivial partitions yield a matching and a toroidal grid, and the other fractured graphs also yield quite simple graphs. So unions of matchings and cycles, packings of paths of length 2, just cycles, and also suns, where a sun is a cycle in which every vertex of the cycle has one dangling edge. I won't go into more details here, but just I hope you believe me that those fractured graphs actually have a quite nice form that are easy to analyze. Okay, so let's go back to this result here, and let's apply it to toroidal grids. Okay, so now let H be the toroidal grid of size P. So we have P vertices here and P vertices here. And let K be the number of edges of this toroidal grid, which is 2 times P squared. Then the coefficient of the toroidal grid is just this sum. And you get this if you just evaluate this, this sum, and you end up with this. Okay, so, and you see those correspond to the fractured graphs. So the M2P squared, for example, corresponds to the matching of size 2P squared. As I said before, the important thing here is we only have this many terms, and this holds for any K. So for every prime P, we actually have this. And even if the primes grow, the graphs H, the toroidal grids grow, but the sum still has only that many terms. Now let's take a look what happens if phi is actually the property of being planar. Okay, so the matching is planar, matchings and cycles are planar, path packings are planar, cycle packings are planar, and sun packings are also planar. So even without defining like in detail how those graphs look like or how large they are, just believe me, all of those are planar. However, the graph H itself, corresponding to the partition where every generator is in the same block, this graph is not planar. And in other words, the toroidal grid is not planar, but we have already seen before that it is actually a torus. So this graph has genus 1 and it is not planar. And therefore, if we evaluate the sum for planarity, we get that it's -1 modulo p. So what we just have seen is that in this linear combination, the coefficient of the toroidal grid of size p for prime p is always non-zero. So to sum it up, we have the following. For every phi and k, we can express our problem as a linear combination of homomorphism counts. For the property of being planarity and toroidal grids of a prime number of size, the coefficients are non-zero. By complexity monotonicity, we have that our problem for planarity is at least as hard as counting homomorphisms from toroidal grids. But since toroidal grids have high tree width, we get by known results on the complexity of homomorphism counting that the problem must be sharp W1 hard. Okay, and this is how you do it for planarity, but actually for any minor closed property, you can follow a similar approach. Sometimes you need other graphs, other Cayley graphs than toroidal grids, but essentially it's the same idea. The important thing is that the number of generators is small. Okay, so let me conclude with the last slide. First, I'd like to point out that the conditional lower bounds under ETH, we don't get them by toroidal grids. Also for planarity, toroidal grids don't suffice for the ETH lower bounds. Instead, we use Cayley graph expanders. Our approach does not only apply to counting KH subgraphs that satisfy a property, but also to related counting problems. For example, we analyzed a parameterized variant of the Tutte polynomial to which it applied. And by now, we also know that it applies to the problem of modular subgraph counting. And then the big remaining open question is, of course, the question whether we can find a complete classification of this family of problems for any property phi. Again, in this talk, we have seen that for minor closed properties, we get an explicit condition which is sufficient and necessary for being fixed parameter tractable, but we don't know that yet for not necessarily minor closed properties. So it would certainly be very interesting if a similar classification holds true for indeed any graph property phi. Okay, but that was everything I wanted to show you, and the time is almost up. So thank you very much for watching, and perhaps we see each other in one of the Q&A sessions. Goodbye.